because my advisory reference. All right. The famous farmer problem. Farmer wants to build a pen out of 480 yards of fencing. He will be dividing the pen into 3 sections that are all equal in size. What dimension should he make the pen to maximize the area? There is a phrase in here that is most essential to the problem. In fact, it drives the entire problem. Maximize the area. Yes, very good. It's equal also drives the problem. But maximize the area, that's the whole point to what we're doing. The whole point. So optimization, to optimize something means to run it most efficiently, right? If you want to run at an optimal level, you're going to run at the peak level. So when we're doing optimization problems, we want to find a lot of times maximums or minimums, and we know that through calculus. What do we know about local maximums or local minimums? What do we know about those? How? The slope is 0. The derivative is equal to 0. Very good. So I like my 4 boxes piece, and this is how I'm going to operate. I'm going to model the problem. I have 3 sections. I have width, length, and length. This should be reviewed from last year, so I'm going to go through this pretty quickly. I would now like to write down some formulas or some relationships that exist here. Any ideas? Got a couple. Excellent. The second box is a lot of times the most difficult part for people to come up with, and that's where the real practice happens. People know how to draw, people know how to eventually write the equation and solve the problem, but at the end of the day, this is what we need to do, okay? We need to come up with some interesting pieces here. I have an equation that has 2 parts to it, the width and length. But that doesn't have anything to do with area, okay? This drives the problem, so I should also write something else down. What do you want? Area equals length times width. Very good. So I'm going to write a function for area because calculus allows us to deal with functions very well. I'd like to be able to deal with this area piece right here, but I have 2 variables. Can I solve for 1 variable? Yeah, I have 2 equations that both have L and W, so I can solve. As a matter of fact, I'm going to say 2L is equal to 480 minus 4W. And I'm going to divide by 2, and I'm going to get L is equal to 240 minus 2W. Now that I've solved for that, I can substitute, and I will have an equation, rather a function, area in terms of which variable? W is equal to 240. I didn't get the 40 out before he said 2W. So times W. So all I did was I took this, okay, and I substituted it in for L. So now I do have a function. Area in terms of width is equal to 240 W minus 2W squared. Okay, but as soon as you get here, you guys, you should always think of this, okay? As soon as you get a function, you have to be able to think of 3 parts of it. You know, what would it look like if you looked at it on a table? What does it look like as a graph? What does the algebra look like? So this is a parabola that's upside down, okay? The graphical representation is essential to what we're doing. So if we're looking to maximize this problem, which part of the parabola are we looking for? The maximum. It's referred to as the vertex. We have ways of finding the vertex, negative b divided by 2a, but we could also recognize that, as you said before, the derivative is equal to 0 at that spot. So if you want to find the maximum, the easiest way to do it is to simply take the derivative and set it equal to 0. So what is the derivative of this? (240 minus 4W, or 4W equals 240. And so W is equal to 60. So let's make sure we answer the question. What dimension should he make the pen? Width is equal to 60. How do I figure out the length? Very good. Plug it in right here. Length is 240 minus 2W, or 120. Done and done. Now, a lot of people, when they set out to do this, what they want to do is they want to make a bunch of these shapes and multiply it out and see what gives the biggest area. That's a lot of trial and error, isn't it? We used calculus to find this very quickly. Very quickly. Yep. Anytime you're trying to do optimization, you're always looking for a maximum or a minimum. And so, therefore, that's what we do. Okay, let's do another one. Farmer builds a fence against a barn. There's my fence. Got a lot of grass in there. I've got a some type of mutant animal that's living in my pen. I have no idea what it is. It's a cat pig. So, so I'm going to label this width, length. You tell me. Give me a formula. Very good. 2W plus L is equal to 320. What's driving this problem? It says maximize area. No, you will not always maximize. In this problem, we want to maximize area, though. So, area is equal to width times length. Length times width. Solve for L. L is equal to? Sure, you could write an area in terms of length if you want to instead. You'll come up with the same answer. So, I'm going to write an equation or function. Area in terms of what variable? Width is equal to 320W minus 2W squared. That's what happened when we took this, plugged it in for L. What does that graph look like? Upside down parabola. So you are looking for the vertex, the maximum, the point at which the derivative is equal to 0. What is the derivative of that function? 320 minus 4W. 4W equals 320. W equals 80. So if W is equal to 80, the question again says, what dimensions should he make? Plug it into this portion here. Length is equal to 320 minus 2W, so L is 160. Have you seen enough of the farmer problems? You saw them last year, you've seen them this year. I'm guessing you could do any of them, correct? Flip it over. Let's try something more interesting. A box with an open top. So if it has an open top, how many sides does it have? 5. Open top is to be constructed from a piece of cardboard that is 10 by 18. Okay? You're going to cut a square from each corner and fold it up. Find the largest volume that the box can have. What is the phrase that generates this problem? Find the largest volume. Maximize the volume. That's what drives our problem. You already know what equation you're going to need. Volume equals length times width times height. Very good. So now we have those 3 variables. So we're going to have to do some substitution here. Important that we draw the problem correctly. Let's model it. We have 10 by 18. Yes, you have seen this problem before. I basically took a lot of the pre-calculus problems you had last year and put them back in here. Okay? So, fill in the pieces. Can you see, what should I label something here? Why do those all have dimension x by x? Because you're cutting out a square, yep. You see that when I cut those out and I fold up the sides, and when I say the sides, I'm talking about, folding along that line. Do you see that I will end up with a 5-sided figure? Okay? So we want to maximize the volume. When I maximize the volume, I now need to represent these dimensions. And so I have length, I have width, and I have height. Can you tell me what is the length of this box going to be when I fold it up? (18 minus 2x). Everybody see where I get the 2x? What is the width? 10 minus 2x. The height is x. So, I do have an equation, a function for volume in terms of which variable? X. Okay? So I'm going to take the height, which is x, and multiply it by 18 minus 2x, and multiply that by 10 minus 2x. If you took the derivative of that right now, what rule would you have to use? The product rule. So let's write it out as a polynomial, so we can use the power rule. So v of x is equal to, what's 18 times 10? And then times x will be 180x. 18 times negative 2, and then negative 2 times 10, so negative 56, and it will be an x squared. Negative 2x times negative 2x, 4x squared times x, 4x cubed. So now we have a function for volume in terms of x. X is also just the same as the what? Same as the height, so the height of that box, okay? So, you could write v of h as well. What shape does this make? Yeah, it's a cubic. It's going to look, is it right side up or upside down? Right side up. What is the y-intercept? 0. So just think about it, okay? We're going to use our graphing utilities to help work through these problems, but Isaac Newton, in order to do this, he would then have to, if he wanted to sketch the curve, he would then have to do what we did back in section 4.5. He would have to do the curve sketching process as well. So, not all of it, but in this situation, it does pass through 0, 0. Okay, so it looks something like that. I have no idea if that's, I don't know if it, crosses the x-axis 3 times or not. Well, actually, I do. Well, I'm sorry. Let's just look at the problem here. Look at the problem. It crosses at 0, it crosses at 9, and it crosses at 5. So 0, 5, and 9. So it does cross at those spots. So 0, 5, and 9. You don't have to do that for these problems. I just want to let you know. We do know that because it's already in factored form. So our answer is going to come between which two numbers? 0 and 5. So in order to find that, that's where the derivative is equal to 0. So let us take the derivative. What's the derivative? Oh boy. Does not factor. You could take out a 4, but outside of that, we really got nothing left. Nope. 6 doesn't work. So we would use the quadratic formula, correct? Don't do it by hand. Take your calculator, use the quadratic formula. Somebody punch it in, what do you get? Who's got it? And Anderson's got it for us. Type it in correctly. Yes. There should be two answers. Well, just hold on. 7.27. I just want you guys to recognize that it does give us both, so that you would understand what's happening here. Okay. Obviously, which one do we choose to use? We choose that one. It's concave down. That's how we verified it. So we could take, Isaac Newton could take the second derivative and be able to find that you're concave down and concave up. Therefore, you know that you're supposed to use this one. Also, it's the only one that fits within the problem. 7.27 doesn't work if you plug it back in. If you were to cut 7.27 off of each part, yeah, exactly. So a couple ways to make sure you're doing it correctly. So x is 2.06. What was the question? Ooh, do we have the largest volume? No. So what do? Right. What we have to do is we have to take v of 2.06. So we have to plug 2.06 back into our function. Okay, you got it? 168? So 168.13 inches cubed is the largest volume that you can have. You should. Okay, let's move to number 4, something much more interesting. Dimensions. They give the largest area. Yep. So we know right away we're going to have area equals length times width, or base times height. In fact, for this one I'm going to use base times height. That's going to make more sense to us as we look at the problem. Whose base is on the x-axis and whose corners are at or on the parabola y equals 12 minus 3x squared. So let's try to get a good picture of what's happening. 12 minus 3x squared. What does that look like? Upside down parabola shifted up how many units? 12. Has a y-intercept of 12, and it's going to head down from there. If you found the x-intercepts, you would know that they were -2 and +2. That's not essential to this problem, but just in case you were curious. So what we're going to do is it says we're going to basically kind of inscribe a rectangle. Its base is along the x-axis. Chapter 5, so we're still in 4. But the infinite rectangle thing is, we don't. But we do know this. We do know this because the parabola is symmetrical about the y-axis. We do know that the rectangle is going to be the same on, the width is going to be the same on the left as it is on the right from 0. So, okay, so here we go. This whole point here, xy really drives the problem, okay? As far as setting up. So this is kind of the trick that people have to see, okay? Can you tell me if this is the coordinate xy, what is this length right here? X. So the base is going to be what length? 2x. Because you're going to go x in each direction. The height is going to be y. Except now what we have is we have two variables. We have x and y. We only want one. Could you express y in terms of x? Very good. Y is equal to f of x. Or what is the function? 12 minus 3x squared. If you wanted to figure out, just think about it for a second here. Okay? Let's say that x was 1. Okay? Let's just suppose x was 1. You were 1 unit over, and you wanted to know how high that would be on the parabola. What would you do with 1? You would plug it in. You do 12 minus 3 is 9, so you'd be 9 units high. So if we have an x value, the way we figure out the height is we plug it into the function. So therefore, your height could simply be written as what you guys said, 12 minus 2 or 3x squared. So now we can write a function for the area in terms of what variable? X, and it's equal to what? So 24x minus 6x cubed. Okay, now hold on. What does the graph look like? It's a cubic, right side down or upside, or right side up or upside down? Upside down. How about this? What's the y-intercept? 0. So if I draw this graph, a quick sketch of the cubic, it looks like it probably looks something like that. And we're trying to maximize the area. So we're going to look for that point right there. Okay? That's what we want. Well, that happens when the derivative is equal to, what is the derivative? 24 minus 12x squared. Excuse me. How do we solve that? Oh. If we square up both sides, we get 2 over the root of 3, or 2 roots of 3 over 3. And that can be plus or minus, right? So is my graph correctly represented? No. In fact, now that I take the derivative, I can see that the graph, and this isn't extremely important, I just want you guys to have an idea of graphically what's happening here, is the graph probably looks something more like this. Okay, where you have the minimum on the left side and the maximum on the right-hand side. So we found x is equal to 2 roots of 3 over 3. The question was, what are the dimensions? If x is 2 roots of 3 over 3, what should the base be? So x was 2 roots of 3 over 3. What's the base then? Double that. Very good. So 4 roots of 3 over 3. And how would you figure out the height? You would plug it in. What? Oh, I'm sorry, not 4 roots of 3. 2 roots of 3. 2 is our x value, that's what we plug in. 8. Is says find the dimensions that give the largest area. So those are the dimensions that give the largest area. What do you think about that? Yep. Like that one, Casey Gilbertson? All right. One more for today. We've got through 5. That'll put us in great shape to get through the other 3 on Monday or Tuesday or Wednesday, depending on when we have school again. Yeah. I don't believe that the Albert Lee District in the past 20 years has ever made up any school days due to snow. So I think that the district has the right to do that, but I don't think it'll happen. Okay, boys and girls, this one's a little bit more involved. We're gonna really have to focus here. Okay. Rectangle is inscribed in a semicircle of radius 16 inches. What should the dimensions of the rectangle be in order to maximize the area of the rectangle? We know, again, that area of a rectangle is equal to length times width. But getting the picture down is a little bit more difficult. If I draw my little coordinate plane here, and I mark off 16 because that's the radius, and negative 16 and positive 16, oh, have I shown you how I can draw a perfect circle? I'll show you on Monday. Yep. Do the arm thing. We'll do it. Okay. So I'm going to inscribe a rectangle. Call this X, Y. Instead of length times width, for this problem we'll talk about base times height, so it makes more sense to you. A for the day, what's the base equal to? 2x, because you're going to go x in each direction. Very good. How about the height? Oh. Okay, we know the equation for a circle with radius 16. Okay, that's fine. You lose 2 points. All right. Watch, folks. Watch very closely, okay? Would you agree that the circle, you always know that you have this radius equal to 16. You also have a y value. You also have an x value. That makes a right triangle, does it not? So you tell me the equation for a circle now. X squared plus y squared equals r squared, which is the same thing as the Pythagorean theorem. Okay? So that's all you need to think about. So we have x squared plus y squared is equal to r squared, which is 256. Is that a function? No, it is not. Is our semicircle a function? Yes. It is the top part of the circle, right? The positive portion. Very good. So we solve for y squared. We have y squared is equal to 256 minus x squared. Now what? Square root both sides. A lot of people like to square root 256 and square root x squared. Totally illegal. So nope. Yep, so we have 256 minus x squared, the square root of that quantity. Okay? That is our function. So that's the height. So, as we do our equation, we have area in terms of what variable? X is equal to 2x times the root of 256 minus x squared. You guys do see that when you took the square root, you get the positive and the negative. The negative would be the under part of the circle, and the positive is the upper part. Okay, so this is what we have. Now, do you know what that graph looks like? I don't know either. We could, do, at this point, maybe Newton would do the whole process of curve sketching and figure out what it looked like. If I'd have my graphing calculator, just to be sure, if I was, if I had to be right on this problem, I would definitely try to come up with the correct graph so I could see what it looked like. We're not going to do that. But what we do have to make sure we do is take the derivative properly. I might run out of room to write. You might too. We'll see what happens. But let's take a prime of x. If I take the derivative, what do I have to use? Very good, Larry. Product rule incorporated with the chain rule. What's the derivative of 2x? 2 times the root of 256 minus x squared. Plus 2x times the derivative of 256, or square root of 256 minus x squared. Chain rule. Set it up. U to the 1/2, 256 minus x squared. Derivative of u to the 1/2 is 1 over 2 roots of u. Derivative of 256 minus x squared. And 2x multiplied, the 1/2 and the 2 will cancel. You'll be left with simply a negative x over the root of 256 minus x squared. So that's what we get when we take the derivative. Let's set it equal to 0. 0 equals 2 roots of 256 minus x squared minus 2x squared over root of 256 minus x squared. Now what would you like to do? I think you have a couple options. You can find common denominators, create one, and then set the numerator equal to 0, or you could simply move this portion to the left-hand side and cross multiply. That's what I'm going to choose to do. 2x squared over the root of 256 minus x squared is equal to 2 roots of 256 minus x squared all over 1. Let us multiply. 2x squared times 1? 2x squared. Root of 256 minus x squared times root of 256 minus x squared. 256 minus x squared, distribute your 2 through and you get 512 minus 2x squared. Now what? 4x squared equals 512. Divide by 4. X squared equals 512 divided by 4 is 128. Root. Very good. 11.3. Square root of 64 does come out if you want to write it in that way. You don't have to, but you could reduce it to 8 roots of 2 if you so chose. And you said 11.3, Emma? Okay. I would accept either on the test. It really doesn't matter. Okay. So yes, we have the positive or the negative. Obviously, you can see that in this problem. Whoa, where'd the problem go? There it is. We, are going to take the positive, and so therefore, you solved. You got x is equal to 8 roots of 2, or 11.3. So, very good. The base is equal to 16 roots of 2, or 22.6. And the height, now you see why I wrote it as the root of 2. So that'd be really fun when I would plug it back in here, right? And this is the most common problem. I already made this mistake. When you plug it back in here, do you plug in 16 roots of 2 or 8 roots of 2? 8, because that's what x is. So 8 roots of 2 squared is 128. We already figured that out. 256 minus 128? 128. And the root of 128? 8 roots of 2. It wasn't a proof, so technically we should be able to do that, but it's just kind of fun to, you know. Yeah, it's because we're cool. So, all right, good times, huh? All right, so these type of word problems, we did the same ones at pre-calc last year. Now you can do them using calculus. Then we'll try some more complicated problems. So we kind of give you the easy dose first. Give you your homework. Okay, this is your assignment. I want you guys to know as you do these problems, the book has it divided up in sections A, B, C, D, E, and F. Basically, just do what we did, okay? Don't worry about answering all the questions. Come through like you should. I do want you to know that one or two of these problems is not exactly like how we set it up in class, okay? 7 and 8 and 22 should follow exactly with how we set it up. These just, you know, look, that was really bad. Just a little twist to the setup.